Okay, we're ready to go over 5D worksheet for the Math 4 class. All right, for your first question, you had to do the table for average temperatures in Raleigh. And your graph should have looked something like that on Desmos after you put your table in. And we've got a listing there of what all of the values should be. Now, let's see now, they asked you to write the sinusoidal function for this. So we're going to take, this is that same box. And so we're going to say y, whoops, I got to turn my pen on. Y equals 19.98, you might as well call it 20, sine. B was 0.4779, we'll say it's about 0.5. And then C was, this is going to be x minus C, which is x minus 3.7. And then D represents plus 68.8, roughly. All right, so what is the period of the function? Well, the period of the function is we're going to have to take that number 0.477799 and say that equals 2 pi oh, wait a minute now, no, excuse me, I got it backwards. We want to find the period, and that ugly decimal goes down here. So let's see what the calculator says. So when we check with the calculator, we get something resembling that, 13.15. Now, hang on a second here. Wasn't the original data the months of January through December, 1 through 12? How do we get a period of 13? The only thing I can figure is that it doesn't account for the month of 0 or something like that. That is the only thing that I can figure that makes sense in this situation. All right, there's a relationship there, and we're just not spotting it right away. All right, what is the amplitude of the function? The amplitude would be 20. What does it mean in the context of the problem? Well, we're talking about 20 up and 20 down. So that means that in the course of the function, there's a variance of 40 from absolute top to absolute bottom. Now I want you to look at the temperatures on the data chart. Let's see now, our biggest one is 89.1 and our smallest one is 49.8. That's about 50 and that's about 90. They're 40 apart. So it makes sense that from tip top to absolute bottom, the difference is 40. Because when you've got your line going through the middle here, that's 20 above and 20 below. That's a difference of 40 from top to bottom. So that's what's going on there. That's why that makes sense. Okay, let's move on to number 2. We have the monthly precipitation in inches for San Francisco. And so when you plug in that table, your graph is going to look something like that at the bottom. And notice the R squared value is 0.9575, which means this is really, really good stuff. This is fairly close to the curve itself. Now, write the model of best fit. So we're going to say y equals, and we're going to call that 2.5 sine. B is going to be about 0.4. Then x minus negative 4.3, that's going to be x plus 4.3. And then we're going to go up 2.3. Now, I have to ask this question. How does the 2.3 fit into this data? Well, the 2.3 represents the vertical shift, right? We're doing, 2.3 would be roughly right about there. Something like that. Does 2.3 represent a number of value in this discussion? If we're talking about average monthly precipitation across 12 months, where do you think the average is going to lie? Right down the middle, right? 2.3 actually represents a fair estimate of what the average precipitation across the entire year. If you say, take the entire all 12 months and add them up and divide by 12, you should get about 2.3. So that represents what the average rainfall would be for any given month. Now, true, in San Francisco, they seem to dance on either side of that. Nobody seems to be fairly close to the 2.3. It's either way up or way down, but that's California for you. All right. Now, this one is a bit of a challenge. So we have the data on how many minutes it takes for a cup of coffee to cool down after it's been poured at 179.5 degrees. And of course, you think about that. Oh, there's that lawsuit where somebody spilled hot coffee and they sued McDonald's and stuff like that. So McDonald's had to create regulations on serving hot coffee just to prevent themselves from getting further lawsuits because people are going to be stupid. Quite honestly, people are going to do things that when you're handed a cup of hot coffee, these are things you don't do. But yeah, there are accidents. But anyway, so the first thing that I ran was the sine. And, you look at the R squared, 0.9968, that's really, really good. That's really, really close to the line. All of those are right on that line. But I have a problem with this. You see where the curve is going? It bottoms out and then it starts raising up again. Is a cup of coffee after you pour it really going to start getting hotter again? That's not real world realistic. I just don't see that happening. So I'm sort of thinking that the sine graph may not be the way to go. Now, we did plenty of other regressions. So I thought to myself, this kind of looks like a parabola. I wonder if a parabola would turn out any differently. And so I ran it as a parabola. And it actually turned out to be the exact same R squared value, 9968. But again, we're having that bottom out, and at some point the coffee starts getting hotter. That's not real life. That's not going to happen. If you leave the coffee sitting in a cup on the counter long enough, it's not going to start warming up again. So I said, all right, well, let's try our logarithm. We seem to see a lot of situations where the logarithm was helpful. Now, these were degrees in Fahrenheit, correct? And so 32 degrees Fahrenheit is freezing. And so 32 would be right about here. And I'm noticing that my coffee is getting colder and colder, and now it's starting to freeze. And I'm still not quite happy with that. This is heading in the right direction. This is the right idea, but that's not where this is going to go. So I said, all right, well, we did sometimes do exponential. Let's try exponential. Look at that R-squared value. Instead of 9968, this is 9977. This is actually a better fit than any of the others. Not to mention the fact that look at C. C represents the vertical shift, right? 71.9, you might as well call that 72. It's like there's this asymptote sitting at 72, and the line is not allowed to cross it. Now, wait a minute now. If I've got a cup of coffee sitting out on the counter at McDonald's, why would it level off at 72? That's because 72 is room temperature. Eventually, your cup of coffee is going to cool down to whatever the ambient room temperature is, and so that would be 72. This is a perfect fit. This makes sense. And so, we're going to use this. This is going to be, winner, winner, chicken dinner. If I want to project, the cooling rate of my coffee or whatever, this is the guy I'm going to want to use. So if we've got our model straight, now we start to address some of the other questions. When is the coffee at a temperature of 108 degrees? And so I had to go on, trace along the line until I found 108. That's about, without zooming in closer, that's about as close as I was going to get. And so, this is in terms of minutes and degrees Fahrenheit. So I would say, when is the coffee at 108 degrees? I would say about 11 minutes. That's when the coffee should cool down to 108. That was not exactly one of our data points, so we can't, pull from our data set and find the answer there. We're having to extrapolate based on our newfound friend here, the exponential curve. All right. So the next question is, talked about the lawsuit at McDonald's. Should be served at 155 degrees to avoid serious burns. After pouring the coffee, how long should they wait? And so the question really becomes, how long before it drops down to 155 degrees? Well, again, I'm tracing this curve and I'm blowing it up until I can get reasonably close to 155. And again, this is in terms of minutes and degrees Fahrenheit. And so this is telling me that I need to wait at least 3.357. I'm going to say either 3.5 minutes, maybe 4. If you're worried about a lawsuit, let it go to 4 minutes. So, and it's stuff like this that when McDonald's, they make rules for everything. When you're in that kind of a business and handling fast food like that, you have to have procedures and policies for everything. And so, they are probably teaching their, the crew that runs the registers. They are usually the ones that pour the coffee. And so they're teaching them that it has to sit there for 4 minutes before you can serve it to them. If it's pouring out at whatever 179.5 degrees, I think it was initially. Yeah, I think, yeah, that's the last one. So we're good to go there. But that's showing you how you can use these regression models to make projections. But at the same time, you actually witnessed firsthand a perfect example of, looking at the way that the curve is shaped, and is that realistic in the real world? And if it's not, then I should be considering one of my other options. And so in this case, we wound up with exponential. It doesn't surprise me because we talked about one point about Newton's law of cooling with logarithms, and so that's where I began. When I started thinking about coffee that's cooling, I remembered Newton's law, and so I wondered if this is either a log or an exponential. And the log didn't work as well, but the exponential sure did.